Regularized regression controls complexity while keeping a linear prediction function. A regression tree takes a different route. It divides the predictor space into regions and assigns a constant prediction within each region. This simple construction can represent non-linear relationships, thresholds, and interactions without asking the researcher to write every transformation in advance. The price is a discontinuous prediction surface and potentially high sampling variability. Imagine forecasting household expenditure from income and family size. A tree might first split households at an income threshold. Within the lower income group, it might split again by family size, while the higher income group receives a different split. The prediction in each final group is the average expenditure among training observations in that group. One predictor's role can therefore depend naturally on another predictor's value. Formally, the tree partitions the predictor space into non-overlapping terminal regions. For any new input, we locate the region containing it and report the mean outcome of training observations in that region. The fitted conditional mean is a step function. This local averaging connects trees to non-parametric regression, but the data determine both which variables define the regions and where their boundaries are placed. The method, called classification and regression trees, or CART, builds this partition through recursive binary splitting. Starting at the root, it looks at every eligible predictor and every candidate threshold. Each candidate splits the data into a left group and a right group. For a continuous outcome, CART picks the split that most reduces the within-group residual sum of squares, which is the same as making the two child nodes as pure as possible. The process repeats separately inside each child node. Because later splits can differ across branches, the tree automatically represents interactions. A threshold on inflation may matter only when unemployment is already high, for example. The algorithm is greedy. It chooses the best split available at the current step and does not revisit earlier choices to find a globally optimal partition. That limitation is important for understanding tree instability. Growth stops when a rule is reached, such as a minimum number of observations in a node, a maximum depth, or an insufficient improvement in fit. A deeply grown tree usually fits the training sample closely. Tiny leaves can reproduce isolated outcomes, but their averages are estimated from little information. Training error, therefore, keeps falling even when future prediction begins to deteriorate. Pruning controls this complexity after a large tree has been grown. Cost complexity pruning balances residual sum of squares against a penalty proportional to the number of terminal leaves. A small penalty favors a large detailed tree. A large penalty removes branches and yields a shallower model. Cross-validation chooses among the nested, pruned trees, using held-out prediction error rather than visual preference. The bias-variance trade-off is especially visible in trees.